Uh, okay, good. So from Southeast University, he will talk about solvable irrelevant deformation with boundaries and defects. Okay.
Okay.
Yeah, please.
Thank you. Okay. Can you hear me? Okay. So I'll start anyway. So first, I would like to thank the organizers for this for organizing this workshop, and it has been quite nice. And you are doing even for the second time. So today I'm going to talk about some recent work where we study TTbar-like irrelevant solvable deformations in quantum field theories with boundaries and defects. So this is based on the work of together with Florian Lebert from Humboldt University and also Deliang Zhong from Tel Aviv University, and the paper just appeared this morning. So one thing I want to mention is that actually this work was initiated from the previous workshop. And in this sense, I think this workshop is doing a great job in initiating discussions and collaborations. And I hope it will keep doing so. So let me start with some motivations and some reviews. So in the past few years, we have seen that TTbar and other irrelevant solvable deformations like TTbar deformation have been intensely studied. And these studies have deepened our understanding about quantum field theory and integrable models. So this we can already see from yesterday's talk. So for example, we are now learning deeper about the CDD factors from Tiago's talk, and also non-local dipole QFTs from Monica's talk. And also for integrable models, we are learning that the ODIM correspondence can be deformed by TTbar deformation and still keep this match from Roberto's talk. So all this is very nice. On the other hand, we know that both in quantum field theories and in integrable models, there are extended objects like boundaries and defects. So these objects, they're very interesting for several reasons. First of all, we know in real physical systems, the boundaries and defects are everywhere. So it is interesting to study them, in particular for some questions like the Kondo problem. And from a more formal point of view, these boundaries and the defects actually contain a lot of information about the bulk physics. And also, once we introduce boundaries and defects, we can have other interesting observables like the boundary entropy, the boundary free energy, and also some boundary one-point function. So in fact, right at this moment, I think there's a workshop going on about QFT with boundaries and defects. So this shows it is a very active direction. So given this importance of defects and the boundaries, and also the progress in TTbar deformation, it's a very natural question to ask. So how does TTbar and other deformations affect this structure? So this is the question we are answering. And in this talk, I will investigate this problem in the context of integrable quantum field theory. So here I want to stress that the fact that we are working on integrable quantum field theories is a technical convenience. Actually, some of our results, I think it works also for non-integrable QFTs, like many of the results in TTbar deformation without boundaries. So before going to the boundary, let me give a brief overview of integrable quantum field theory. So a quantum field theory can be described in several different ways. The most standard way is to introduce a Lagrangian and an action. And then you go and quantize this Lagrangian and then compute observables, usually perturbatively. Of course, you can study integrable quantum field theories using explicit Lagrangian. However, for many purposes, in particular, if you want to obtain non-perturbative results, it is often very convenient to use the bootstrap description, in particular in integrable quantum field theories. So the idea is that instead of looking at the Lagrangian, let's focus on the S matrix. So integrable model, they have infinite amount of conserved charges, and therefore they are very symmetric. They have a large symmetry. So this severely constrains the dynamics, such that any m particle interaction is factorized to a sequence of 2 to 2 scattering. So basically, it means that the 2 to 2 S matrix encodes all the dynamical information of your integrable QFT. So then the idea is clear. If we can find this 2 to 2 S matrix non-perturbatively, then we can just, then there's a hope we can solve this theory, and we can use this information of the S matrix to compute other observables, like the finite volume spectrum and also the correlation functions. So this is the logic. So we will focus on the S matrix. And this description is particularly convenient for TTbar deformation, because from the past few years, we learned that under the TTbar deformation, the S matrix is deformed in a very simple way by multiplying some CDD factor. So this is very convenient to use it and to study from this bootstrap approach. Now, how do we determine the 2 to 2 S matrix? So the idea is via the bootstrap axioms. Namely, we impose a system of equations that should be satisfied by any reasonable S matrix, and then we try to solve these consistency relations. So we have the unitarity and the crossing symmetry from the usual S matrix bootstrap program. So here each black dot denote 2 to 2 S matrix. So here you should understand it as some equations for the S matrix. Now for integrable model, crucially, in addition to unitarity and the crossing, we also have the Yang-Baksa equation. Basically, this is saying that, okay, so the 3 to 3 scattering is factorized into a sequence of 2 to 2 scattering, but the factorization order does not matter. So this is a consistency relation from integrability. And then you go and write down a set of equations for this S matrix, then you try to solve it. So of course, you need to make some analyticity assumptions about the S matrix. Once you do that, you can indeed find non-trivial solutions in a number of very important cases. Now, in this story, actually, it's an interesting story about the CDD factor. In the early days, CDD factor is called CDD ambiguity, because these guys are basically a set of functions that automatically satisfy this condition. So if you take any healthy S matrix and multiply by the CDD factor, then the deformed S matrix still satisfies this condition. So in the early days, people just regard these CDD factors as some slightly annoying ambiguities, which we just want to fix and get rid of. But nowadays, with the progress in TTbar deformation, we have a much better understanding about the CDD factors. So they are not just some annoying factors that you want to get rid of. Actually, they are related to very exciting UV physics. And I think we will learn more about this in the coming years. But it's fair to say the importance of CDD factor now become clear now. And this is a continuation of the S-matrix bootstrap approach. So once we determine the 2 to 2 S-matrix using this bootstrap way, then we can find, for example, the spectrum by integrability. So in particular, we can use beta ansatz, and we can also use thermodynamic beta ansatz in the finite volume. And the correlation functions can be computed by the form factor bootstrap approach. So there are nice stories about these subjects. So this is the bulk story. Now I go to the boundary. So suppose we put a boundary at x equals to 0. So this is a left boundary. And then I define my quantum field theory on the right half plane. So you will have, if you want to do a Lagrangian description, you can write down the action and integrate only on the right half plane. This is the bulk Lagrangian. And then you can also have a boundary part, which lives only on the boundary. So this is the boundary Lagrangian that describes the degrees of freedom that only lives on the boundary. So notice that in a field theory, actually you can place the defect either in the space direction or in the time direction. So if you place this defect in the different direction, you will have a seemingly different description, but they are equivalent. So for example, if you place the boundary in the space direction, like here, then these boundaries really enter as boundary conditions for your fundamental fields and other quantities. So suppose you want to compute a m-point correlation function, then you just sandwich this operator between two vacuum states, where this vacuum state is defined as the vacuum state of the half line. On the other hand, if you put your boundary in the time direction, then this boundary manifests itself as a boundary state. So this is denoted by B. And if you want to compute the correlation function, you sandwich it between a boundary state and a vacuum state. And this vacuum state is the vacuum state of a full line of the whole system. So it's nice to keep this in mind, that we have different descriptions, but they are equivalent. Now, as I said, this is just the boundary for, this is a generic boundary condition, but for integrable field theories, there are specific boundary conditions that preserves integrability. So now I'm going to discuss these special boundary conditions. So the study of integrable boundaries in integrable quantum field theory was initiated in the paper by Gosho and topological. So we start with the bulk integrability. If a quantum field theory is integrable, this means in the bulk there are infinitely many conserved currents. So these are the conservation equations. So we have T and theta and T bar and the theta bar. And this index S runs from 1 to 3, 5, and to infinity. So there are infinitely many of these conserved currents. Now we put a boundary. So suppose that x equals to 0. So suppose this combination, if I evaluate this combination with this current at the boundary where it's x equals to 0, if this combination at the boundary can be written as the derivative of certain function, which is the boundary potential for infinitely many s, then we call this kind of boundary condition an integrable boundary. Because if this condition is satisfied, then you can construct a conserved charge, which is preserved by the boundary. So suppose infinite many conditions like this are conserved, are satisfied, then it means you can construct infinitely many conserved charges that are preserved by the boundary. So this is the integrable boundary condition. And as I said before, if we want to compute things non-perturbatively, it's very convenient to use the bootstrap description. So to this end, we need to change our mind and imagine the particle picture, where you have a lot of particles interacting with each other. So in the bulk, these particles just scatter among themselves. And this scattering process is described by the bulk S matrix. Now, if you have a boundary, there's an additional possibility. So you can take a particle, and the particle will hit this wall and get scattered back. So this is the scattering of a particle against the boundary. So if our boundary is integrable, then this scattering is purely elastic. So it just gets reflected. And because the boundary condition is integrable, so all the even charges are conserved. So by even charge, I mean the charges which are even under parity. For example, energy is one of these conserved charge, because if a particle hit here, and if the scattering is elastic, then the energy of this particle should be the same. But on the other hand, we see apparently momentum is not conserved. It flipped a sign. So all the odd charges are not conserved, but the even charges, which are like the energy, is conserved. And to describe this kind of scattering, we need another quantity, which is the boundary as matrix. So to summarize, if we introduce the boundary and we want to use the bootstrap description, then we need to specify what is the boundary as matrix. So how do we determine the boundary as matrix non-perturbatively? The idea is exactly the same as in the bulk. Namely, we can impose a set of bootstrap axioms. For example, we have the boundary Yang-Buxer equation. So here again, each blue dot in the bulk is the bulk as matrix, and each black dot at the boundary is the boundary as matrix. So this is an equation involving two bulk as matrix and also two boundary as matrix. So this is a boundary version of the Yang-Buxer equation. And in addition to that, we also have boundary unitarity condition, and we also have the boundary crossing condition. So all these axioms are proposed by Gaucho and Zamolodchikov. So then you can write down a set of equations that involving both the bulk and the boundary as matrices, and you will sit down and try to solve it. So again, by specifying some analyticity conditions for the boundary as matrix, you can actually solve find a non-perturbative solution about the boundary as matrix, and in a number of important examples. And then once you have both the bulk and the boundary as matrices, you can again go and compute other observables like the spectrum and the correlation function. So in the boundary case, as I mentioned in the beginning, there are some new observables, such as the boundary free energy and the exact tree function, which is also called the boundary entropy, and also the boundary one-point function. So the structure is much richer, and all these deserve further exploration. So finally, let me briefly mention the defect case. So this is the integrable defect. So again, in the Lagrangian description, we have the same story. You can write down a Lagrangian, and then you can write down a defect Lagrangian describing the defect. So here I would just focus on the bootstrap description, because that's the one we need. So you can also define the notion of integrable defect, namely the defect that preserves integrability. So this study was initiated by Tofino, Musardo, and Simonetti. So what is the difference between a defect and a boundary? So if you have a boundary, then you take a particle and hit the boundary, you can only be reflected. But if you have a defect, there's a chance that you can go through. So there are two kind of processes. One is the transmissive, and the other is the reflective. So to describe these two processes, we will need to determine two quantities. One is the transmission amplitude, T, and the other is the reflection amplitude, which we denote by R. And so about the defect, it's actually important to distinguish two kinds of defects. So one is called topological defect, the other is non-topological defect. So in terms of integrability, integrable defect, The topological defect just means purely transmissive. So if you have a defect that if a particle hit it, it never gets scattered back, it just goes through and picking up some phase vector. Now this type of defect is called topological. Otherwise, it's called a non-topological. So it is topological in the sense that if you have a purely transmissive defect, you can place your defect in any place of your theory without causing any energy. So you can basically distort it and place it anywhere you like. And about this topological and the non-topological defect, there's a useful fact, which is a theorem proved by Castro, Alvareto, Fring, and Gerham. They show that actually only free theories can have integrable non-topological defect. So this means if you take any interacting integrable model like sine-Gordon, and then you require the defect to be integrable, then you have only two choices. Either you have a purely reflective defect, which is the boundary, or you have a purely transmissive defect, which is topological. And the defect that allows both transmission and reflection, they can only exist for free theory. So these are two theories, free fermion and free boson. So later on, we will see that topological and the non-topological defects, they get deformed in a different way under the TTbar and the more general deformation. So this is the first part of the story. So basically, I introduced the bootstrap type description of quantum field theories with defects and boundaries. So the new ingredient is simply the reflection as matrix and also the transmission and the reflection amplitudes in the defect case.
Yufeng,
Yes.
can I ask one question?
Sure.
In the case with the transmission and reflection together,
yeah,
is there any other new Yang-Baxter equation? Just boundary Yang-Baxter, or?
Yes. So actually, in this case, you can write down a similar defect Yang-Baxter equation. Because you have several choices, so the defect Yang-Baxter equation is more complicated. You need to distinguish different cases. And so you have more equations. And that's why this equation seems to be more constraining and leads to this theorem.
I see.
Okay. Now I will go and discuss how to deform, how this structure gets deformed under the TTbar deformation. So I will start with the boundary case. So as we said before, the boundary preserves even charges and does not preserve odd charges. So let me describe in slightly more detail what are the even and odd charges. So again, we start with the bulk. So in the bulk, we have this conserved current, as we said before. And from this conserved current, you can construct integrals of motion, which we denote by IS and I bar S. And then you can take a combination of IS and I bar S. You can define the HS and the PS. So this PS or P type of conserved charge is like the momentum. These are the odd charges. So in fact, if you take S equals to 1, then it's the usual momentum. And these HS are the even charges. If you take S equals to 1, then this is the usual Hamiltonian. So this PS is broken by the boundary, and the HS is preserved by an integrable boundary. For each conserved charge, we can associate local conserved current. So for example, for the HS conserved charge, I have a conserved current, K mu. So the time component is the charge density. Well, the space component is the current density. So we have a similar current for the PR type, conserved charge, which is broken by the boundary. So then, using two conserved current, we can construct so-called bilocal deformation. So this is so first we construct a bilocal operator by taking an antisymmetric combination of two conserved currents. And then this is my deforming operator, and I can put it on the right-hand side. So this is the definition in the Hamiltonian description. So since we are now concerning boundaries, so here I just place as left is the left boundary and as right is the right boundary. So I integrate in this region. So let me comment that R, if I take R and S equals to 1, namely if I take the Hamiltonian current and the momentum current, then this operator is precisely the TTbar operator. So TTbar deformation is a special case of the general bilinear deformation. So to study the deformed S matrix is convenient to introduce another deformation, which is almost equivalent to the bilinear deformation. So this is called the bilocal deformation. So the definition is as follows. We take in the Lagrangian formalism, the deformation is defined on the right-hand side by a commutator of some operator x with the Hamiltonian itself. So this deformation actually is an algebra preserving deformation. So it was first investigated and used by Bakir, Beisert, and Löbet in 2012 in the context of integrable spin chains. So they are using this deformation to find integrable deformations of quantum spin chains in a systematic way. And as we learned, also cited by Monica's talk from yesterday, I think in 2020, Yuri Krusov and Onkar Parikh also used this type of equation to study the state, to study the deformed eigenstate. And also in Monica's talk yesterday, she made heavy use of this type of deformations to study the TTbar deformed Virasoro algebra. So as we can see, this type of deformation seems to underlie different corners of TTbar-like deformation. So I think this is something quite general and powerful, and it definitely deserves more investigation. So if you take any x, this will preserve the integrability. But of course, in order your deformed Hamiltonian takes a nice form, we need to specify to some special x. So here, I will choose this x to be a bilocal operator. So it means that I have two charge densities, PR and HS, at two different spacetime points. And I integrate over them with the constraint that x1 is smaller than x2. So you have two locations, that's why it's called a bilocal operator. So these two deformations are actually related like this. So in a finite interval, this commutator, you can compute it, and after some very simple manipulations, you can find that they are almost equivalent up to these boundary terms. So here this JPR is the current density at the left boundary, and JHSR is the current density at the right boundary. So suppose we are in the infinite volume where you can ignore these terms, then these two deformations are really equivalent. So for the boundary case, let's consider, say, we place the boundary on the right, we place the right boundary, then we can push this SL to infinity, and we can forget about this term. And on the other hand, we know that since the even charge is preserved, so there cannot be some non-zero flow of this current at the boundary, so we can also forget about this term. So in this semi-infinite system, in this semi-infinite volume, these two deformations are really the same. So we can either use this or use this to study the deformed S matrix. And it turns out to be more convenient to use a bilocal construction. So here I just want to make one comment is that in the bulk case, it's not so important that the order of these two operators, PR and HS, when you write down the bilocal deformation. But in the boundary case, it's rather important to keep in mind the ordering. So if you have a right boundary, then this HS must be on the right. This is a small subtlety concerning the boundary case. And as I said, this bilocal rewriting is very convenient to use to derive the deformed S matrix, as I will show in detail now. Okay, so how do we deform the S matrix? Let us start with the undeformed story. So I will start with the bulk, and then the boundary and the defect case will be started in more or less the same way. So to consider the bulk 2 to 2 S matrix, we first consider two-particle state. So this contains this asymptotic state, where here we have two particles, the red particle and the blue particle. So the red particle is moving faster than the blue one, and it will scatter, and finally you have the outgoing state asymptotically. So these two states, which are drawn out, are the asymptotically ordered state. So namely, these two particles, you should imagine that they are very far away from each other. And also here, they are very far away from each other. And of course, there are contributions where these two particles are close to one another. But this contribution does not affect the S matrix. So that's the point. Because the S matrix, by definition, is given by the ratio of this coefficient in front of the outgoing state and the ingoing state. So it's only the ratio of this A, of these two A's. So this gives the bulk S matrix. So it's not that these contributions are not there, it's just they don't contribute to the S matrix. So we will ignore them in the following, but we need to keep in mind that they are there. Okay, so this is the undeformed story. So then we want to do the deformation. So under the deformation, this ordered state, because this ordered state, they are basically just, these particles are far away, so they are basically just plane wave. And so they are not deformed. But the coefficient in front, this A, they get deformed, and they will become lambda dependent. So the strategy is to find this deformed A, and then compute the ratio. So this will give us the deformed S matrix. Then how do we find this deformed A? So the idea is to write down a differential equation. So to do that, we start with the eigenvalue equation. So we take this deformed asymptotic, take this deformed two-particle state and the deformed Hamiltonian, which is so this state is the eigenstate of the Hamiltonian. So it has this eigenvalue where HU is just the energy of each single particle. Now I have two particles, so I take the sum of two particles. Here it's important to notice that this H, it does not depend on lambda. And because we are in an infinite volume, so here we are considering the system in the infinite volume. Now, as we know, TTbar and the other irrelevant deformations, they change the UV behavior. So they will change the finite volume spectrum, but they will not change the infinite volume spectrum. So it's important to keep in mind that this H, because we are in the infinite volume, so they are not changed. So this is the undeformed H. And then we just take the right-hand side and to the left, and we take the derivative with respect to lambda, which is the deformation parameter. So here, this derivative of lambda will hit h lambda, and so we can replace it by this commutator. And also, this two-particle factor, this two-particle state, we can plug in this. So then by some simple algebra, you find the following equation. So indeed, on the right-hand side, because this derivative of lambda will hit this a lambda, so you have a derivative of a lambda with respect to lambda. So the idea is that we can work out the left-hand side, and then this will give us a differential equation for a lambda, which we can solve very easily. So this is our goal. So now we need to, so actually it's rather easy to argue that the ordered state is an eigenstate of the bilocal operator as follows. Because the bilocal operator is defined like this, so you have two charge densities. And these two particles, they are far away from each other. So when you act this, this operator on this type of state, you have two kinds of contributions. So the first kind is that this operator, this density, charge density, acts on the first particle, and this density acts on the second particle. So this will give you, because they are far away from each other, so they can be approximated by some single particle state. So this just gives you this vector PR, which is the eigenvalue of that, and the HS is some, which is the eigenvalue of this type. And then you also have the possibility where both operators acting on one of the states. So this I will just denote this type of contribution by FRSU and FRSU prime. So it's not important to specify the form because they will get cancelled in the final result when we compute S matrix. So we just remember this comes from the contribution when both density act on the same particle. So that's our result. We act this on two ordered states, and we get this. So plugging this back here and compare the two sides, we obtain a solution. We can obtain an equation for a lambda, and we can solve it easily. And this gives us the deformed S matrix. So it is indeed the original S matrix times an additional phase factor. So if we take R equals S, then this is precisely the CDD factor obtained by Smirnov and topological. So this confirms our derivation. And yeah, I just to summarize, I have shown you how to use this bilocal type of argument, how to first rewrite the TTbar as a bilocal deformation. And using the bilocal deformation in the infinite volume, we can determine the asymptotic S matrix, which confirms the other derivations, either from some logical Smirnov or from some gravity type of derivation. And we do the same for the boundary. So before I just review how it applies. So for the boundary case, what we want to determine is the deformed boundary S matrix. So similar to the bulk case, we start with a one particle state because we only need one particle. And you see, here I have a particle moving towards this boundary, and it will get hit by the wall and go back and leaving this boundary. So you can imagine this is an incoming state, and this is the outgoing state. And the reflection matrix is just given by the ratio of these two coefficients. So then, similar to the previous case, we can deform under the deformation. So this one particle state is deformed, where this A becomes lambda dependent. So basically, we want to find this A. And we play the same game and take derivative of the eigenvalue equation. And after some manipulation, we have this equation. And then we can write down the differential equation for A lambda, and we obtain the deformed boundary S matrix. So the result is, again, the boundary S matrix times some phase factor. And if you take R equals to S, this again looks like a CDD factor. So a confirmation of our result is this paper by Roberto and collaborators, where they considered the boundary S matrix in CFT in the context of effective string theory. So there they find that they conjecture that it's also a phase factor. And if we take R equals to S equals to 1, this confirms their result. So it's a consistency check. Now, interestingly, for the boundary, we can do something fun. So we can, apart from taking this X be a bilocal operator, we can actually take it to be an odd charge. So this is a specific deformation for the boundary case, because suppose you are in the bulk case without boundary, then this PR, which is the odd charge, it just commute with the Hamiltonian. So if you plug in this commutator, it basically doesn't deform anything. So you cannot perform this kind of deformation in the bulk. But now you have a boundary. And we know that the boundary does not preserve this guy. So we can just plug in this, this X as the PR. And then we can also obtain the deformed boundary S matrix. So for this case, it only changes the boundary S matrix and leave the bulk S matrix invariant. This deformation is very simple. It's just a phase factor, and the phase factor involves the PR eigenvalue. And as we'll see, this also has some funny interpretation when we study the spectrum. Now we come to the defect case. Here I will be rather brief because I have discussed two cases in detail. So in the defect case, first consider the topological defect. So the asymptotic state is the following. You have a particle moving towards the defect, and then it goes through and then leave the defect. So you have the sum of these two terms. And the transmission amplitude is given by the ratio of the two terms. And we do the deformation where A and B will depend on lambda. And we solve the differential equation. We take derivative, we solve for A and B. We will obtain the same equation. Then we can solve for A and B. But the funny thing is, we find that A and B are deformed in precisely the same way. So then if you take their ratio, the transmission amplitude is not deformed. It's precisely the same as the undeformed transmission amplitude. So I think this should be physically very reasonable because these defects are topological. So we know by definition, something topological is not sensitive to the metric. And we know the stress energy tensor is the variation, corresponds to the variation of the metric. And TTbar deformation is triggered by this stress energy tensor. So the topological defect is not sensitive to the metric and is not sensitive to the stress energy tensor. So it's not sensitive to all this kind of deformation. So I think it's physically reasonable that the topological defect is not affected by this deformation. On the other hand, the non-topological defect, you have this kind of state. You can go through or you can be reflected. And then you have the transmission and reflection amplitudes. So going through the same computation, we find that the transmission amplitude, which is the topological part, is not deformed. But the reflection amplitude, which is the non-topological part, is get deformed. And it gets deformed in the same way as the boundary S matrix. So this is some nice result. So by now I have tell you how TTbar and general bilinear deformation changes the S matrix both in the bulk and in the boundary and also for the defect. So then I will go to the last part of the talk, which is using this information to actually compute physical quantities. Now, the first quantity that pops in your mind is for sure the spectrum. So I will start. So this is the finite volume spectrum. So suppose I put my quantum field theory on a strip where I have two boundary conditions, left and right, and the distance between the two boundaries is denoted by L. So, in integrable quantum field theories, it's very important to distinguish two regimes. One is the large volume limit, and the other is the finite volume. So the reason is that the large volume limit is much simpler than the finite volume because we don't need to care about finite volume correction. So if you are in the large volume limit, basically, the spectrum is well described by the so-called asymptotic Vedanta. So this is the logic is as follows. Now, in the scattering picture, you should imagine the Hilbert space of the theory contains one particle state, two particle state, three particle state, and n particle state. So if you consider an n particle state, because you are in a finite volume, then the momentum of your particles should be quantized. And the quantization condition is precisely the asymptotic Bethe-Ansatz equation. So it involves the bulk S matrix, and it also involves the boundary S matrix. Here, S left and S right are just the left and right S matrices. So this is the Bethe equation. So in principle, we should know, if I give you a theory, then I will give you the bulk and the boundary S matrices, and then you should go and solve this equation and find this rapidities or momentum. After you do that, you plug it here and compute the energy. So this gives you the spectrum. So this HUJ is just the energy of a single particle with rapidity UJ. So then what we need to do is quite simple. To see how the spectrum gets deformed, we just look at the asymptotic Bethe-Ansatz equation. So let's start with the bilocal deformation. So if we take the bilocal deformation, which include TTbar as a special case, we know how the S matrix got deformed. So this is the bulk S matrix, you have this factor, and the left boundary and the right boundary, you have these factors, where here PR and the HS in the relativistic quantum field theory is just given by this simple factor. So we see that PR is indeed odd, and HS is indeed even. And you just plug this deformed S matrix to the quantization condition here, and you do some, so here, let me mention two comments. First, if I take R equals to S, then the Lorentz invariance is preserved, and what we have is the TDD factor. But if you take R and S different, then typically this deformation does not preserve Lorentz invariance. Then we are in a situation more similar to the TTbar deformation. So it's just one comment. And another special case is that if you take R equals to 1, namely here, PR, I just take this PR to be the momentum. I take just a momentum and a higher charge, higher even charge. Then this deformation is also special because it has a very interesting hard rod picture interpretation. So let's start with this case. So we take R equals to 1, and then so this is a special case, and then we know the deformed S matrix. We plug in the Bethe equation, and this is the deformed Bethe equation. So it has a very interesting structure. So basically, the difference is here, the red part. So we have an exponential factor, which involves minus 2I lambda times Qn, and so this Qn is nothing but the conserved charge. It's nothing but the conserved charge of this HS in the n particle state. And this conserved charge is coupled to a momentum Puj. So if we look at the original Bethe-Ansatz equation, we see that this momentum Puj is coupled to the length L. So we can bring this back to the left-hand side, and then we can write this equation in the same form as the original Bethe-Ansatz equation, but just modify the length. We modify this length to be L plus lambda Qn by the amount of conserved charge. So we have seen this modification of the length in the bulk case, in the TTbar deformation. That is from solving the Burger's equation, where the radius also changes. So here we see that this length is the distance between the two boundaries, and they also got changed in this deformation. So if you know that the length is changing this way, so this will imply that the flow equation for the deformed energy is given by this. So if we take S equals to 1, then this is a TTbar case, and this is En, and we precisely obtain the Burger's equation, which is consistent with previous results. And so we see the change of effective length. So this has this very cute dynamical hard rod interpretation. So this was first found last year by Kadi and Doyon, and at the same time by myself. So the interpretation of this change of length is as follows. So under this special dynamical hard rod deformation, each particle, point particle, become a finite size hard rod. And the length of each rod is proportional to its charge. So here, if we take lambda negative, then the rod length is minus lambda times hs. And because your particles becomes hard rod, so the free space between the hard rods are decreased. So it becomes smaller. And this is given by L plus lambda Qn. So if we take the other sign, this just means the distance between the particles are increased. So, so the effective length is also increased. So this is the intuitive picture to keep in mind, which correspond to the dynamical hard rod deformation. And what about the more general case? So I don't take this R equal to 1 anymore, I take it to be PR. And so for this case, we can similarly write down a set of a flow equation, but because we have this PR, so it's more convenient to introduce a twist which couples to this PR, and you will see why. Because if we write down the deformed Bethe-Ansatz equation, we see the phase factor will combine together to give this. So now you have this charge Qn coupled to PR instead of P. So in order to bring it back to the original form, I would rather start with something that with a twist nu, which couples to PR. So then I can just bring this back, and at the price of shifting this chemical potential by this amount. So this will give me the flow equation, which is similar, but here instead of taking derivative with respect to the length, which you can imagine to be the twist of this momentum, I take the derivative with respect to the twist. So this is the only difference. And we also have this case where X is the odd charge. Now in this case, as we said before, the S matrix is not deformed. The bulk S matrix is not deformed, but the left and right boundaries are deformed. So again, in this case, if you take R equals to 1, namely if you take it to be the momentum, it's a special case. Because in that case, you find the deformed Bethe equation is just the undeformed one by shifting this L by the amount of lambda. And so in this case, we have this funny thick wall picture. So namely, the boundary becomes thicker by the amount of minus lambda divided by 2. And if your wall is thicker, then the free space between these two walls are, of course, smaller. And if you have the other sign of the deformation, then the effective distance between the two walls are increased. So you see this increasing and decreasing the distance between the two walls, it only involves the boundary. So this is something specific to the boundary. It doesn't change anything in the bulk. But still, it affects the spectrum in a very simple way. Basically, you don't have a nonlinear flow equation, so it's all linear flow equation. This is the story for R equals to 1. Now, if you take R larger than 1, then you can write down a similar linear flow equation. So, so this is the story for the deformed spectrum. We see that the flow equation for the finite volume spectrum is very simple. So the summary is that we analyze the spectrum in the large volume limit, and by looking at the boundary Bethe-Ansatz equation. Now, from our experience in the periodic boundary condition, we know that these flow equations for the spectrum are actually quite robust. They don't care about which volume you are working in, right? So they should be, if they are valid in the large volume, they should also be valid in the small volume. This is the case for the periodic boundary condition. And we also expect that it should hold here. Actually, for the TTbar deformation, we don't, it should also hold for non-integrable quantum field theories. That's our expectation. So with that goal in mind, we just go to the finite volume. So in the finite volume, you need to take into account finite size corrections, and this becomes a much more complicated problem. But nevertheless, we can apply the boundary thermodynamic Bethe-Ansatz to compute the finite volume spectrum. So it's most easy to compute the vacuum energy. But if we look at the vacuum energy, if the flow equation is the same as the large volume flow equation, then already this confirms our conjecture. And we just use this method by Leclerc, Mosado, Thaler, and Skorik. The only thing that is slightly different from the traditional boundary TBA is that since our deformation involves higher charges, so it will be convenient to introduce twists in the beta equation at the beginning, and these twists are related to the chemical potential in the mirror channel. So pictorially, it's like this. So if we want to do a boundary TBA, so you first place the boundary in the space direction, and then we can take the time direction to be a very large circle. So I identify these two. So at the beginning, you'll put the twist for the quantization condition, and you need to put the chemical potential in your partition function. So the whole idea is that this partition function, this cylinder partition function, can be computed in a mirror channel. So the mirror channel is obtained by performing a double weak rotation. And you see, after this double weak rotation, the chemical potential in the original channel becomes the twist. Well, the twist becomes the chemical potential. So they swap their role. And this was first found in the paper of Hernandez, Schiffley, Negro, and Franzrini in the torus case. So here we generalize it to the cylinder case, but the logic is similar. So you see here we have the chemical potential here, which involves HS, and then this we have the twist here, which becomes the chemical potential in the mirror channel, and this is HR theta. With this in mind, we can just carry on with the usual boundary TBA approach. So I think due to time limit, I will skip most of the details. And so after following the standard procedure, you can write down the boundary TBA equation. And so here the driving term is affected by this twist. And this driving term comes from the boundary as matrices, which is related to this K. So finally, after some analysis, you can bring the deformed TBA equation in this form by shifting the chemical potential or the twist in the same way as in the large volume limit. And for r equals 1, again, we are shifting the length instead of the chemical potential. So finally, we confirmed our conjecture very nicely by using the TBA approach in the finite volume. So these equations are for the ground state, but nevertheless, they match exactly the ones in the large volume limit. So I think it's fairly easy to convince ourselves that this should be a kind of universal flow equation for the spectrum. And because the spectrum flows universally, we can write down the flow equation for the partition function. But we can only do that for the moment. We can only do that for the TTbar deformation due to some technical difficulties, and it takes this form. And the result we derived matches nicely with the one already derived from Cuddy, but from the random geometry point of view. And from this equation, actually, it's straightforward to derive a flow equation for the exact P function or the boundary entropy. So this I will not give more details. You can read the paper if you are interested. Okay, so let me conclude. The conclusion is that we initiated the study of IQFTs, of TTbar deformation with integrable boundaries and the defects. And we have found the deformed S matrices using the bilocal rewriting. And we find that in the boundary case, it's also interesting to consider the odd charge deformations. And in the defect case, we found that we have a topological defect, which is not deformed by all these deformations. So there are a few questions which we can think about in the future. One is about general boundary condition, because I said I believe this flow equation, at least for the TTbar case, it holds for any economic theory, and I think that's true. And in integrable models, we can also consider some boundaries that is not necessarily integrable. And then we can try to compute other observables. For example, we can compute the defect and the boundary correlation functions by the form factor bootstrap approach. And we can also consider some other theories like boundaries in CFTs and defects in CFTs, and also in systems like gas with boundary. So with that, I will end my talk. Thank you very much for your attention.
Questions?
So here you talk about this general boundary. So you are probably you have in mind the general PCFT. So for that, probably you don't need to impose some integral. Well, I don't know, some integrability or what I mean.
Mm-hmm.
So in general, I mean, what do you mean by this TTbar deformation for the just general PCFT? Does it require some condition on the boundary, or it can just can you do the TTbar deformation or of any PCFT?
I think if we just consider TTbar and not this higher charge deformations, then I think you can just require the boundary to be the usual conformal boundary. Then you can derive you can do the TTbar deformation, and the flow equation should be the same as what we're seeing here. Yeah. Because the stress energy tensor is in every healthy theory, but this not necessarily this higher conserved charges. So that's what I mean.
Can you say again the last comment?
So I want to say that TTbar deformation is probably much more general and goes beyond integrability, because it was triggered by stress energy tensor, and stress energy tensor does not depend on integrability. But these higher charges, they will depend on integrability. So they are more specific to integrable systems.
I see. So for example, for arbitrary BCFT, no. So in general BCFT, you don't have a higher charges, so you cannot, in general, you cannot do the deform by higher charge. Is that what you mean? Or?
Well, in some cases you can. I'm just saying, yeah, even without the CFT, you can do that. You can do the boundary.
Yeah. Okay. Thank you.
Yes. So are you considering only diagonal scattering theory here?
I can't hear you clearly.
Yes. So it seems that you are considering diagonal scattering theory.
Yes.
Like X matrix is a diagonal.
Yes. But I think from the derivation, it's clear that I think the boundary S matrix or the bulk S matrix, you can consider any type of how complicated scatterings, but this phase factor will always be the same. They are deformed. They are deformed.
Conserved charges. What happens if these conserved charges can depend on this internal Kala numbers, Kala charges?
Yeah.
Then such that, say, for example, boundary S matrix non-diagonal, but still your result is valid?
I would conjecture yes, although I have not performed the computation. I think it would be interesting to confirm that if you have this internal degrees of freedom, and then you probably need to analyze the nested Bethe-Ansatz equations and so on. This hasn't been done, but I think given the robustness of this flow equation, I would think that some form of this flow equation should still hold. Otherwise, it's a bit strange.
Okay, thanks.
English, Matthias.
Hello, Matthias. I couldn't hear anything.
Can you hear me now?
Yes, now I can.
Yeah, okay, maybe I didn't know that right. So you said in the beginning, you said something about the new interpretation of the CDD factors. I didn't quite understand that.
Okay.
I mean, they have a long history, and
Of course.
I guess the understanding was initially they were a nuisance, but I guess now it's usually interpreted as some kind of, yeah, I mean, containing the details of the dynamics in the cross channel related to dressing factors and so on. So, but my impression was you wanted to say that there was yet a new. I mean, what do you mean by the importance of CDD factor become more clear now?
Okay. So what I have in mind is the following. So previously, basically CDD is some ambiguity you want to fix and you want to get rid of. Now suppose you take S matrix and you multiply by a CDD factor. Before it was not clear what you are doing if you just multiply by a CDD factor. And now it becomes clear that if you do this thing, if you do such a thing, you are performing a TTbar deformation to your theory. And your theory is most probably no longer well defined as a local quantum field theory. It's some TTbar deformed theory. So in this sense, I mean, at least the meaning of TTbar deformation is more clear.
Okay, I see.
Yeah, I would add maybe that, you know, not just TTbar is the typical example, but it seems like the CDD factors are related to some irrelevant perturbations. Most naturally would be TTbar, but you know, you start with your favorite theory, you start adding some irrelevant interactions, and that's supposed to lead to a CDD factor.
Yeah.
Which is kind of a new, certainly, you know, in the early days, people didn't think about that.
Yes, yes, and I think that that's really a very nice progress where we understand the meaning of this, what you are doing to the field theory.
Mm.
I agree.
Any other questions or comments? Okay.
Excuse me. So you said so the boundary entropy of the deformed boundary QFTs can be computed. So
okay, please
so
finish.
can you compute the entanglement entropy of the deformed boundary QFT by using the integrability?
Mm-hmm. Okay, so I think you are asking about the entanglement entropy, right?
Yes, yes.
Okay, so first of all, let me clarify something. When I say boundary entropy, so actually this means the exact G function, which is the overlap of the boundary state and the vacuum state. So this is called the boundary entropy because it counts the degrees of freedom on the boundary, and it's slightly different from the entanglement entropy that we usually say, where you need to trace out some part of your Hilbert space and then define the von Neumann entropy. So for that, we can, because we have integrability formalism to compute that quantity, so we can write down the flow equation and then we can try to solve it. This is the G function story, which I didn't say in detail. Now, coming back to the entanglement entropy, the honest answer is not clear. but I think maybe it's easier to investigate in the defect case, because usually, say in CFT or some other quantum field theories, if you want to compute entanglement entropy, usually you compute the correlation function of some operator, right? And so correlation functions is very difficult in TTbar deformation. So even now, we don't have like a very good understanding about correlation functions in TTbar deformed theories. So Cuddy has say, a flow equation for correlation functions, but it's not particularly explicit, such that we can extract useful information from that. But in the boundary case, I think you can compute the twist one-point function with boundary. So this should be easier than computing a two-point function. So even from the form factor bootstrap point of view, you only need one form factor instead of two. So I guess this might be a better starting point to understand how the local operators get deformed and so on. But to your question, my understanding is no. I don't know.
Thank you.
Other question? Okay, if not, let us thank the speaker. So this is today all the talks are over, and tomorrow we don't have any morning session. So we start in the afternoon. Okay, see you tomorrow.
Today we will have backend, and you saw the terrace on the first floor.